Hey guys, this is 7.6. We're going to be looking at solving systems using matrices, primarily with Gaussian elimination. So first of all, what is a matrix? A matrix is a collection of numbers and a collection of numbers arranged into a fixed number of rows and columns. A matrix can serve as a device for representing and solving a system of equations. To express a system in matrix form, we extract the coefficients, of the variables and the constants, and these become the entries of the matrix. When a system is written in this form, it's called an augmented matrix. So let's see how you can represent these systems as augmented matrices. First of all, your equations need to be in standard form. So notice that I have my x's first, then my y's, and then on the other side of the equal sign, I have my constant. So it has to be written like that before you write this as a matrix, Your x's, then your y's, then on the other side of the equal sign, you have your constants. Okay, and then from there, you're just gonna get the coefficients. 2, -1, 18. 4, 3, -5. And some people like to draw a dashed line here just to remind them that there was an equal sign there. But you don't have to. That's an augmented matrix. Let's do it again on number 2. So notice we've got the equations in standard form, x, then y, then z, equals your constant. Okay, so writing that as a matrix, taking my coefficients, 4, 1, 8, 13, 5, 10, -5, -20, -1, 3, 13, 27. And if there were a variable missing completely from an equation, like let's say this y hadn't been there at all, you would want to put a 0 as a placeholder there. Now you could also go the other direction. If you're given a matrix, you could write the equations, right? So I would know, just looking at this matrix, that I have 4x plus y plus 8z equals 13, because that's how an augmented matrix works. The first column is the coefficient for your first variable, the second column is the coefficient for your second variable, and so on. So you can also go in reverse from there. Usually we're taking the equations and making a matrix though. All right, so that's how you write a matrix, and that's what a matrix is. Now, Gaussian elimination is a process that you can use to solve systems of equations. In order to do Gaussian elimination, you need to understand matrix row operations. So let's go over those. For any augmented matrix of a system of linear equations, the following row operations will result in the matrix of an equivalent system. So all that's saying is you can do any of these 3 row operations and you will not change the matrix. You're going to change the way it looks, and you're not going to change the system. You're going to change the way it looks, but you will not change its value. It will be an equivalent system. Okay, so first of all, you can interchange any 2 rows. You can make row 1 into row 3. You can switch those two, you can do whatever like that. So up here on number 2, I could take row 1 and switch it out with row 3. I can switch those around. These are rows. These are columns. Okay, you can switch rows, you cannot switch columns. You can multiply or divide the elements of any row by a non-zero real number. You can multiply or divide an entire row by a non-zero real number. Okay, so up here, maybe since I notice all of these are divisible by 5, maybe I want to divide that entire row by 5. Sure, you can do that. Since this one has a negative in the front, since this third row has a negative in the front, maybe I want to multiply by -1. I can multiply the entire row by -1, and that will not change the system. Okay, and then the third thing that you can do is replace any row of the matrix by the sum of the elements of that row and a multiple of the elements of another row. So what that's saying is, I could take row 2 here, and I could add 2 of row 3 to it. I could do row 2 plus 2 of row 3. Or you could just add row 3. You can add rows together. You can also add a multiple of a row to another row, and that will not change the system. Okay, so we can switch rows, we can multiply or divide rows, and then we can add rows. Okay, so let's try performing those operations on matrix A. So first I want to switch row 1 and row 2. So here's row 1, here's row 2. I'm going to switch them out. So that's going to become -1, 5, 3, 2, 6, 4. All I did was switch row 1 and row 2. Now, this is the new row 1, and this is now row 2. You switched them, and now we're working with this new matrix A that has this row 1 and row 2. You switched them out, but now they have those new names. So now I'm going to do number 2. We're going to do these consecutively, which I just meant like we're not going to start over with our original matrix. So now I'm going to do row 1 plus 2 of row, that's supposed to say 2. Sorry, row, this is supposed to be a 2 here. I'll edit that in the notes for y'all hopefully. Row 2 plus 2 of row 1 is what that was supposed to say. So we're going to take row 2 and we're going to add 2 of row 1 to it. So row 1's not going to change. I'm only changing row 2. This first, whatever comes first right here when you're adding 2 rows together, that's the row you're changing. I am taking row 2 and I'm adding 2 of R1 to it. So maybe you need to think about what 2 of R1 would be. 2 of R1 would be -2, 10, and 6, if you need to think about that. And then you're adding that to row 2. So I'm doing 2 plus -2, 0. If you need to write that out here, you can also do that within the matrix. You could do row 2, which is 2, plus 2 times row 1. And then in the second column, I'm going to have row 2, 6, plus 2 of row 1, which is 5. And then lastly, I have 4 in row 2, and I'm going to add 2 times 3. Okay, so I'll simplify that. 2 plus -2 is 0. 6 plus 10, 16. 4 plus 6, 10. Okay. And now in in number 3, we're going to take that matrix and we're going to multiply row 1 by -1. So I'm not changing row 2, but I'm taking row 1 and I'm multiplying each entry by -1. So just all 3 of my signs changed. And that's it. Those are the 3 row operations that you can do. There's a special form of a matrix called row echelon form. In this form, you have 1s down the main diagonal and 0s everywhere below that. So 1s down the main diagonal, and then everything below the 1s is 0. You can have any numbers above the 1s. You can have any numbers there above the 1s. That is called row echelon form. And so for Gaussian elimination, a strategy to solve systems of equations, you're trying to get your matrix into row echelon form. You're trying to get your matrix to look like this, where you've got 1s down the main diagonal. You're going to use those 3 row operations that we just learned to get it that way, to make it that way. So if you actually look at the problem that we just did, at the 3 row operations that we just did, you see that I was actually working towards that. When I switched row 1 and row 2, I did that because then that was going to give me at least something close to 1 in that first spot, which it has to be a 1 to be in row echelon form. And then you see in number 2, the reason I did that was to make this entry into a 0, because I know anything below that 1 has to be 0 for row echelon form. And then I multiplied that entire first row by -1 because that first entry needs to be 1. So just with those 3 operations, I was able to get a 1 and a 0 in my first column. A 1 in the first row, first column, and a 0 below that. So you kind of already have a little idea of how that's going to work. We have some steps here to help us out. So given an augmented matrix, you're going to perform row operations to achieve row echelon form. The first equation should have a leading coefficient of 1. Interchange rows or multiply by a constant if necessary. Let's do example 1 as we follow through these steps. So the augmented matrix I have here on number 1 is 2, 3, 7, 3, -4, -32. Now, to obtain a 1 in the first row, first column, there's multiple options that you have, right? You can do any of those, any combination of those 3 row operations that we just talked about. My first instinct here is to switch row 1 and row 2. Okay, so I want to switch those. And then I can subtract this row with the 2 from the row with the 3, and that will give me 1. I know it doesn't say that here as an option, but you can do any of those row operations to obtain a 1 in that first spot. Okay, so I'm just going to switch those around. First, so 3 -4, -32, and then 2, 3, 7. And now I'm going to do row 1 minus row 2, or plus negative row 2. If I do row 1 minus row 2, that leaves me with a 1 here. -4 minus 3 gives me -7. -32 minus 7 gives me -39. Great. The reason I did that instead of multiplying by a constant is because then I would have been left with a lot of fractions to deal with. And who wants to do that? It's easier, it's always easier if you can keep your numbers whole numbers. Of course, keep in mind you could always multiply an entire row by the denominator to get rid of any fractions if you want to. All right, so now that we have a 1 in a row 1, we're going to use row operations, step 2, to obtain zeros down the first column below the first entry. Okay, so I need to make this 2 into a 0, sorry, into a 0. How can I do that? Well, I could do row 2 minus 2 of row 1. And that will leave me with 0 there. All right, so I'm going to have row 1 not changing. Okay, and then I'm going to have a 0 here. 2 minus 2 is 0. And then 3 minus 2 times -7. 3 minus 2 times -7. That gives me 17 in the second column. And then 7 minus 2 times -39. 7 minus 2 times -39. 85. Okay, so that was step 2, get that 0 below the first 1, and then use row operations to obtain a 1 in row 2, column 2. So I need this spot to become a 1. How can I do that? Well, that's pretty simple. I'm just going to multiply by 1/17. I can do row 2 times 1/17. 1 over 17, row 2. So first column not changing. Second column multiplying by 1/17 or dividing by 17. That leaves me with 1. And then 85 divided by 17 leaves me with 5. Okay, and then you just want to continue that process until you have a 1 in your diagonal here and then zeros below that. So we are done with our row reducing here. This is in row echelon form. Now we can actually solve this system because we actually already have one of our variables. Remember, these were our x, y equals a constant. X plus y equals a constant. So in this second row, we actually have y equals 5. Since there's no x's there, 0x, we actually have y equals 5. And that's kind of the point of getting it to this point, is that you have one of your variables. So I know y equals 5. And now I can use this first equation, which is x minus 7y equals -39 to solve for x. So I know y equals 5. I'll plug in 5 for y. And solve for x. So my solution, or my point where those two lines intersect, is -4, 5. And we got that by getting the matrix into row echelon form, which gives you one of the variables, and then substituting that back in to solve for the other variable. Let's do number 2. We'll do number 2, and then that will be it. Okay, so first put this in row as an augmented matrix. So that's going to be 3, -4, 1, 5, 2, 19. Okay, to obtain a 1 in the first column, we could just multiply by 1/3 in the first column. So I could do just 1/3, sorry, in the first row, 1/3 row 1. That leaves me with 1, -4/3, 1/3. Okay, and now that I have the 1 in the first column, I need to get a 0 below that. I need to make that 5 into a 0. And so I'm going to do row 2 plus, or minus rather, -5 of row 1. So row 1's not changing. I'm subtracting 5 of row 1 from row 2, so that becomes a 0. And then I've got 2 in row 2 minus 5 times what is in row 1, which is -4/3. So 26/3. Okay, and then the third column, I've got 19 minus 5 times 1/3. Oops. (52/3). All right, now that I have a 1 and a 0 in the first column, I need to get a 1 right here in row 2, column 2. So always to make a fraction become 1, multiply by the reciprocal. Multiply that by the reciprocal. So I'm going to multiply row 2 by 3/26. 3/26 times row 2. And then you can do the 52/3 if you need to in the calculator. 52 divided by 3 times 3 divided by 26. Okay, so that comes out to 2. All right, and now it's in it's in row echelon form. So we've got x, y, our constant, x plus y equals our constant, and so we've got y equals 2. Y equals 2. And so then we'll use our first row, which says x minus 4/3 y equals 1/3. And we're going to plug in our y to solve for x. Oops, was a minus sign. So I need to do 1/3 plus 4/3 times 2. That leaves me with 3. So x equals 3, y equals 2. The point where those lines intersect is 3, 2. And tomorrow we'll look at how we can also do this with a system of 3 equations and 3 variables.